we started talking about quadratic forms. So we have quadratic forms. Q is a quadratic form, ABC. Of course, I mean ax squared plus bxy plus cy squared. And ABC are integers. We're interested in what numbers these represent. What n are represented. What n can be written as integer valued of these forms, integer values of the forms. And what we saw last time is you can make a change of variables, an invertible change of variables. So last time, if ABCD, did we introduce the language of GL2 and SL2? Then Q composed with this, let's call this gamma, Q composed with gamma represents the same numbers. Represents the same numbers. The same n as Q. Okay? Did you guys do the exercise? We had the exercise to work out what this, so let's call this Q1. Q1. What are the coefficients? This was an exercise from last time. What are the coefficients of Q1? Did anyone work this out? Okay, so let's do it together. It's going to take, 5 minutes. Just a little bit of algebra. All right, so Q1 of xy. This is Q of gamma of xy. Let's see, how should we write this? Do we want the action of, let's say the action of gamma is on the right. So this is xy times ABCD. No, I think I prefer it on the left for what we're about to do. Well, yeah, I prefer it on the left. Let's say xy are a column vector. Okay, so far so good? Is everybody following what we're doing? So this is the calculation. Let's do it. Let's do the beginning of it together, and then I'll ask you to do it on your own. So A, how do I matrix multiply, right? A times x plus b times y. This is ax plus by is the new x vector, x variable, and cx plus dy is the new y variable. In other words, so this is q of ax plus by, comma, cx plus dy. So far so good? All right, let me give you 3 minutes right now to open up this algebra. In other words, Q is A times AX plus BY squared plus B times AX plus BY. That was the X and this is the Y. CX plus DY plus C times CX plus DY all squared. So take 3 minutes, open up this algebra, and I want you to write it as A1 times x squared plus B1 times xy plus C1 times y squared. So collect all of the x squared terms that are going to come up, collect all the xy terms, and collect all the y squared terms. Okay, does everybody know what to do? So where A1 is equal to something, B1 is equal to something, and C1 is equal to something. So take 3 minutes and give me a thumbs up when you're done with the calculation. Or just text, why don't you put in the chat, done, when you're done. Does everybody know what to do? Does anybody not know what to do? Not understand what the question is? Should we do the first coefficient together just to get started? Or everybody's happily working away? Can you write working into the chat so I know you're working? Great. All right, so I'll give you time to do this. While you do that, I'm going to pull out our notes from last time. So we can reanalyze our table. Okay, so give me a thumbs up when you're, or just write done in the chat when you're done. Is anyone done with A1? How are you doing this? Are you opening everything up and trying to combine it together, or are you working kind of systematically? Where are my x squared terms going to come from? The way I would do it is I would look at, I have an a squared x squared times capital A. So that's definitely going to be there. That's capital A times a squared. Then there's little a x cx. That'll give me an x squared term. That comes with a capital B. So that's capital B times AC. And what's the last term for A1? Yep, big C, little c squared. Okay, so it's not so bad. If you kind of, instead of trying to multiply out this monstrosity and then regroup, if you think about what it's going to be before you do too much work. Is it more or less convenient to write A1 as Q of AC? Ah, very good. Very good. You've noticed that A1 will be Q of AC. In fact, what we'll see... Okay, I'm getting ahead of myself. You'll see in a second. You'll see in a second. Yes, so there's a... So Daniel is making an interesting observation, which is that A1 is indeed Q1 of... Q of AC. And that's not just an interesting observation, it is a fundamental observation which we will exploit very seriously in just a minute. That's right, it's not a pattern that continues. Well, it does continue for C, but not B. Okay, so let's just, is anyone done? Is anyone still, write working if you want to keep working, or done if we can regroup. Or if you want more time, say more time. Okay, those that are still working, I'm just going to slowly, don't listen to me, do your own calculation, don't trust me, but I'm going to slowly start to just try to make some progress here. So now we have a capital A. So I'm looking at the xy terms. There's going to be an xy from 2 little ab times a big A. So there's a big A times 2ab from that. Where else do I get an xy? I get a big B times an AD plus BC. And the big C has a 2CD term. Right? And how about C1? So now I'm looking at the y squared. I have an A times, there's a B squared y squared, so that's B squared. What's my B term? How do I get a y squared? That's just the B times D, y squared. And then the C term is D squared. And exactly, Sheik, exactly Daniel's observation before continues here, that Q of AC is A1 and C1 is the original Q at BD. Okay, does everybody see that? Now what I said last time is that there's some kind of interesting duality between changing the inputs X and Y and changing the quadratic form itself. So let me just say that again. I want to leave this visible here. What we said last time, well, we said this, we didn't really have time to go into it. There's a duality. There is a duality between fixing Q and changing X and Y. In other words, to see what values arise, and fixing X and Y and varying Q. So I want to see that in action for exactly the reason that Daniel and Sheik observed here, and I'm sure others. Let's go back to our old friend, the quadratic form from last time. So you remember this table. I want to recover this table. So this was for the quadratic form. Here it is. So back to our example of Q equals 7x squared minus 11xy plus 5y squared. I want to recover all of these values, but I want to recover them from a different perspective. So so we had this table. I guess I'll just reproduce the table. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We threw out the non-primitive points because those aren't interesting. We can learn those values from other values. Where else are we non-primitive? 3 and 6. 3 and 6. 4 and 6 is not primitive. 4 and 6 is not primitive. Okay, these are... Oh, I'm writing and you can't see what I'm writing. All I was doing was... All I want to do is reproduce this picture. So we had these values, 1, 11, 35, I hope these are correct, 73, 125, 191. Well, I could say and so on, but I'm going to give you an exercise. 25, whoops, 25, 55, 35. I guess you could always reconstruct this. I don't have to give this to you for you to do the exercise. 17, 11, 23, 43, 77. 6 we had some trouble with. 6 was 121. And down here was 25 and 43. Okay, so hopefully these are right. Hopefully I've correctly transcribed what we did last time to here. So what I want to do, now there were two other values of q. There was q of 1, 0, which is always a, right? If I said x equal to 1 and y equal to 0, then that always gives me the a value. That always gives me the a value. If I have 1, 0 for x, that always gives me the a value. That's a hint. And then there's another value, which is q of 0, 1, which always gives me the c value, 5. So here's what I want to do. I want to understand all of these things as changing the quadratic form and not changing q. So let's start with, I'm going to call this q0. q0, again, is the form 7, negative 11, 5. Okay? And q0 of 1, 0 is 7, is a. So I want to change q to equivalent q's, but always evaluate it at the same 1, 0. Okay? So, how do I get the value at 1, 1? So the idea is, change q0 to a new form, to a new q, whatever it'll be, and evaluate at the same point, the same base point, xy equals 1, 0. And we should get the value 1. So what's the new form? Well, you want to think about this for a second, or you have any ideas? Maybe this is a little this seems complicated, but you'll see in a second what to do. So we want q of 1, 0 to be, well, or we want we want q of 1, 0 to be q0 of 1, 1. But that means that should be q0 composed with some matrix evaluated. So q0 evaluated at 1, 0 composed with some matrix that gives the value 1, 1. So some A, B, C, D, so that this becomes 1, 1. So can anyone think of, so now we're trying to solve the equation, need to solve A, B, C, D times 1, 0 is equal to 1, 1. Now what is A, B, C, D times 1, 0? This is A and no B's, and C. We need to solve AC equals 1, 1. So what matrix can we use for that? Well, what does A have to be? One, and C has to be 1. Now I need some B and D so that the determinant is still So the determinant is still 1 or negative 1, so it's invertible. So how about just filling it out like this? So if I make this matrix times 1, 0 will give me 1, 1. And so that gives me a new form, so Q should be Q0 composed with this matrix, 1, 0, 1, 1. Now what happens when you compose a matrix? You get new coefficients. The original Q0, let's see, how do I show you all of these at once? The original Q0, so this is, I guess I'll just write 7, negative 11, 5, composed with 1, 0, 1, 1. And so we just need to plug in this formula for A1, B1, and C1. Does everybody see that? So this will be A1, B1, C1, with big A being 7 and big B equal 11 and big C equal to 5 and little a, b, c, d equal to 1, 0, 1, 1. That's right. That's right. If I choose a different B and D, then Q is different. And I have some choices of B and D, but so you'll see. You'll see. So Yukong is right. I made an arbitrary choice here. In fact, if I want, so what is the condition that the determinant, so this was arbitrary, somewhat arbitrary. What is the condition that I need for the determinant of this? If I know that A is 1 and C is 1, what's the condition that needs to be satisfied? The condition is, let's say AD minus BC is 1. It could be negative 1. Let's just make it 1. And we've determined that A and C should be 1 and 1. So A should be 1, 1 times D, and C should be 1. D minus B is 1. Well, A and C are particularly simple coefficients, so it's very simple to find forms like this. It's very simple to find integers whose difference is 1. You give me any D and I'll make a B. But you'll see in a minute when we have more complicated A's and C's, this will amount to, how do we solve, given, if we know what A and C are, how do we find B and D so that the difference is 1? The Euclidean algorithm. That's exactly what the Euclidean algorithm does. It solves this problem for us. So we have the tools we need. Okay, has anyone figured out what A1, B1, C1 are? So I'm going to take 7 times A squared, A is 1, plus negative 11 times A times C, that's 1, 1, plus, wait a second, we don't have to do any of this. We know that A1 is Q, meaning Q0, of AC, so it's Q of 1, 1. And the whole thing that we were trying to do was find Q of 1, 1, and Q of 1, 1 is, right, 7 minus 11 plus 5, which is 1. Okay, that's the easy one. How about D? D is also, C, C1. C1 is also easy. We might have to work a little bit on B. But C1 is also easy. C1 is Q of BD. So that's Q0 of 0, 1. And we know what Q0 of 0, 1 is. It's the value 5, right? So this is I hope you can see. I'm trying to show you. There's a few too many things on the board at once. Who's utterly and totally lost? Can I have a hand? Or let's say a thumbs down if you're utterly and totally lost. And a thumbs up if you're following along. Sheik is writing something. Okay. All right. So Sheik, let me pick on you if I can. I want to determine B1, right? B1 is determined by this formula that we worked out. So all we're going to do is set 1, 0, 1, 1 in place of A, B, C, D, and 7, negative 11, and 5 in place of big A, big B, big C. Sheik, does that make sense? Okay, so let me continue picking on you. What value do you get for B1? And we don't have to do this in our heads. So we have big A, that's 7 times twice AB. But B is 0, so anything with B actually is nice. So this term is gone. So that's 0 plus big B times A times D plus B times C, but little b is 0, so we just get A times D is 1, and big B is negative 11, so negative 11. And what's that last term? Big C is 5, twice CD, that's 5 times 2. Right? C times D is 1, times 2 is 2, and big C times that is 10. Remind me again, where did the matrix 1, 1, 0, 1 come from? It came from our calculation that we want the value of this. So what we're trying to do is change the Q, but evaluate all of the Q's. We want to recover this table from changing Q's, but evaluating all of them at 1, 0. So that's our 7. We can change Q0 to a new Q and evaluate that at 1, 0. So what we want is the value of this new Q at 1, 0 to be the value of the original Q at 1, 1. So what's the change of variables that gets us to 1, 1? Well, it's an underdetermined system. So we just want one value for now. One solution to this. And so this is where we got the ABCD from. Does that make sense, Stefan? Great. And so what's this last term? This last term is C, which we already know is Q of BD, and that's Q of 0, 1, and Q of 0, 1 is just the last term of Q0. So this is the form 1, negative 1, 5. Is there a way to represent Q0 as a matrix so we can do matrix multiplication? In fact, not only is there a way to represent Q0 as matrix multiplication, there's also a way to represent this whole discussion as matrix multiplication. Well, since you asked, let me pause that for 1 second. I'm going to come back to your question, Dipendra. Yes, there's a way to think of Q as matrix multiplication and to think of everything that we're doing as matrix multiplication, including this, including and perhaps especially this. This is something called the spin representation. All right, let me not use fancy words. So what we've done is we've recovered this value 1. Instead of writing it as Q of 1, 1, so this originally we thought of as Q0 at 1, 1, but actually now it's the quadratic form. X squared minus xy plus 5y squared. So this is the quadratic form x squared minus xy plus 5y squared. We've changed the quadratic form. It's not the It's not the original quadratic form. It's the original quadratic form evaluated at 1, 0. So we're going to keep evaluating at 1, 0 while changing what the quadratic form is. Let's do another example. Okay, let's do another example. How can we recover the value? Let's do 5, 3. So another example. Example 2. Or continuing example. So Q0, again, Q0 is 7, negative 11, 5. And we know that Q0 of 3, 5 is equal to 23. Again, you can just plug in, let's check. 7 times 3 squared. This isn't going to be fun to check. I'm going to just hopefully trust you. I have 125, 9 times 7, 63, 3 times 5, 15 times negative 11, negative 165, plus 125, negative 40, 63 minus 40 is 23. Okay, good. So this value is correct. What quadratic form, and again, it's not just one quadratic form, but you'll see soon, I hope, how to move around different quadratic forms. So give me 1, although there are many, Q, which are Q0 composed with some ABCD, so that Q of 1, 0 is equal to Q0 of 3, 5. Okay, let's see if we can understand what the process is. Okay, Q0 is our quadratic form. I want an equivalent quadratic form. I haven't used this nomenclature yet, but I'm about to. So these are all equivalent quadratic forms. I want to evaluate it at 1, 0 and get the value of Q0 at 3, 5. Do you want to take a minute to think about this, or should we do it together? Why don't you type in the chat together or together? All right, let's do it together. Okay, so again, what we want is Q of 1, 0 to be Q0 of ABCD acting on 1, 0. Right? That's what this composition means. The fact that we want Q to be Q0 composed with ABCD means Q is Q0 with ABCD, and we want this value at XY to be the same value as Q0 would take at 3, 5. So now we have a system to evaluate. Okay? And the system is, so need A, B, C, D times 1, 0 to be 3, 5. Well, that means, but what is ABCD times 1, 0? A times 1 and no B's, C times 1 and no D's, that's AC. Same as before. So now we have a matrix 3, 5, and an unknown BD, and we want the determinant to be 1. The determinant of this is 3 times D minus 5 times B equals 1. How do we find integers B and D that satisfy this? Euclid. Exactly. Euclidean algorithm. So this is what we need. In this case, in the interest of time, let's do it a little bit faster than Euclid would do. What do we have? 10 is 1 more than 9, 2 and 1. 6 is 1 more than 5, that's even better. Thanks, Chang. So B equals 1 and D equals 2 will do. And so we have the matrix. So what we see is that Q will be Q0 composed with the matrix 3, 5 for A and C, and 1 and 2 for B and D. This has determinant 6 minus 5 is 1. Okay? And now it's a matter of writing out Q. So Q, we want to not just leave it like this. We want to evaluate it exactly, for which we need our handy calculation here. Okay, let me write it. Let me write these down. This is 7, negative 11, 5, which was the original Q0, composed with 3, 1, 5, 2. Okay, what's the first entry? What's A1 of this Q? Surya? Surya, you were starting to write something? Exactly. The whole point is it's Q of AC. It's Q of 3, 5. And we already worked out what that is. That is literally this entry, the 3, 5 entry that we're trying to unpack, and that's 23. Great. I'll leave some room for the B. I'll leave some room for B because B is, or B1. B1 is takes more work. How about C1? C1 is Q of Sheik, you were saying something? Right. Q of 1, 2. For C1. C1 is Q of BD, and BD is 1, 2. So what's Q of 1, 2? Q of 1, 2 we already have worked out. Q of 1, 2 is 5. So that should be a 5. We can check in a second if that is indeed what we have. Well, we can check right now. This is 7 times 1 squared plus negative 11 times 1 times 2 plus 5 times 2 squared. 5 times 2 squared for 20. So that I get me a 20 here. How about here? 7 times 1. So that's a 7, 20, 27. And negative 11 times 2 is 22. What did I say? 27 minus 22 is 5. Okay, now we have to work out the middle term, which is B1. Take 2 minutes and work out B1 and write the answer in the chat once you have it. And even if other people have already written it in, just write it in so that I know you also have the same thing. So work out B1. We know what big A, big B, big C are. Little a, little b, little c, little d. Work out B1. Okay, we got one answer. Are other people getting the same thing? Okay, Karen got 10. So Sriya and she got 21. Okay, we're getting a variety of answers. Dipendra got 21. That's the first time we've had two of the same. Okay, we're getting a bunch of 21s. All right. Let me give you one more minute for anybody else who wants to. Okay, Adriana's got 21. Karen, you agreed 21. Surya, you're also getting 21. Lenru's got 21. Great. Got 21. Great. Okay. So A is 7. Twice AB is 7. Twice AB is 6. 6 times 7, 42. So I'll just say 42. Minus 11 times AD plus BC. 6 plus 5 is 11. So that's minus 121. Hopefully I'm doing this right. You'll catch my errors. If not, C is 5 times twice CD. This is 10. 20 times 5 is 100. 100 minus 121, negative 21 plus 42 is positive 21.
Hi, Daddy.
So 21. Daddy's busy. Okay? So does everybody get 23, 21, 5? The joys of homeschooling. Virtual schooling, whatever. Right. So what do we got? So look at this. We have a quadratic form Q. Q is the quadratic form 23x squared plus 21xy plus 5y squared. Right? And that new form has the property, well, this, first of all, it has the property that it's equal to Q0 composed with the matrix 3, 1, 5, 2, and it has the property that Q of 1, 0 is, we don't have to do any hard work, you just read off the first entry, 23. Okay? So that this entry 23 can now be explained also as, can also be explained as 23, what was that B term? 21, 5, evaluated at 1, 0. So instead of the numbers changing, the 3 and the 5 and so on, we can change the quadratic form and always evaluate it at the same place. That's kind of the first hint of this duality. That we can change the quadratic form. Instead of fixing the quadratic form and changing x and y, we can fix x and y to be 1, 0, fix xy to be 1, 0, and vary q. And then we still get the same values. And these quadratic forms all represent the same values. Okay? Maybe we should prove that as a lemma. So first let's define what we've been doing. Definition. Quadratic form, so Q1 is equivalent to Q2. Equivalent. If there exists a matrix A, B, C, D. Now, do I want to say narrow equivalence as opposed to wide equivalence? Let's just stick to determinant 1 equivalence. So all of the matrices that we've chosen, we chose them to have determinant 1. We could have just as well chosen them to have determinant -1, and that would give us another equivalent form. But let's say determinant 1. So that's SL2Z. SL2Z are the determinant 1 matrices. So two forms are equivalent if there exists an ABCD such that, let's call this gamma equal to ABCD, such that Q1 is Q2 composed with gamma. In exactly the way we've been discussing. What is SL? SL as opposed to GL, this is the special linear. This is special linear group. SL stands for special linear. As opposed to GL, we used GL before. GL is general linear. So general linear just means invertible matrices, but invertible with inverses in the same type. So for a matrix to have, do you guys know this? What's the inverse of a 2x2 matrix? Let's talk about this for a second. Actually, it's going to be relevant right now. If gamma is equal to ABCD, then gamma inverse is, Kevin, you were going to say something? Or Stephanie? There's definitely a 1 over determinant, but it's not just gamma. You have to do something to gamma. Yes. Great. Great. Everybody knows this. You flip the diagonal entries, D and A. You negate the off-diagonal entries, negative B, negative C. And then I'm off by a scaling factor. Because if I multiply, so if I take gamma times gamma inverse, that's ABCD times DA, negative B, negative C. If I multiply these two together, I get AD minus BC, AD minus BC, negative AB and a positive AB, and DC and a negative DC, and then a negative BC plus AD. That's AD minus BC. And so if I divide by the determinant, then 1 over the determinant, and then this is 1. So that's the identity. Okay? So the point is, if this is a matrix with integer entries, and its inverse is also a matrix with integer entries, the determinant had better divide all the entries. But the only way to divide all of the entries, you see, the determinant itself contains the, if the entries all have a common factor, well, so the determinant, of course, is AD minus BC. And if they have a common factor, then the determinant has the square of that factor. So you can't divide it out unless the determinant is plus or minus 1. So GL2, so the invertible matrices, GL2Z, is matrices ABCD with determinant 1 over the determinant being an integer. And the only way 1 over an integer is an integer, which is, the only invertible integers are plus or minus 1. And SL is the subgroup of this, consisting of matrices ABCD with determinant equal to plus 1. Okay? So we made this definition. I mean, it looks like an equivalence relation, but it's not an equivalence relation. It's only on one side. Is it symmetric? So is our definition truly a definition of equivalence? So question, is this thing an equivalence relation? What do we need for equivalence relations? Reflexive, symmetric, and transitive. Reflexive, symmetric, and transitive. Question, Stephanie? No? What does reflexive mean? Right. Reflexive means that any quadratic form is equivalent to itself. So, is that true? Surya, why? Yes. Exactly. Because this is Q composed with the identity matrix. Let's look at what the identity matrix does. If I put 1 for A, 0 for C, and 0 for B, and 1 for D, then what happens? A and D are 1, B and C are 0. All of these things are gone. All that's left is in the middle is a B. All that's left here is an A, and all that's left here is a C. Okay? So that's the identity. That's reflexivity. How about symmetry? If Q1 is equal to Q2 composed with A, B, C, D, what is, so let's make this an exercise. Exercise. Yes, because it's invertible. Q2 is equal to Q1 composed with what? Okay, so work out what it is. Is it the inverse? Remember, we said that the determinant was going to be 1. We made our definition in the special linear group. So actually, you don't have to divide by the determinant any longer. But you should see this relationship. That's symmetry. And how about transitivity? Q1 is equal to Q2 composed with A, B, C, D. Q2 is equal to Q3 composed with alpha, beta, gamma, delta, implies Q1 is equal to Q3 composed with what? And the magic is that you should be able to explain this thing. This thing is the inverse, as you've guessed. Inverse. This thing is the matrix multiplication. It turns out. This is matrix multiplication. Okay? These are very important exercises. In fact, they're so important. I think I can do this. Let's make this not an exercise but a quiz. So, yeah, let's make this a quiz. Quiz. The difference between an exercise and a quiz, we don't have homework anymore, but we can have quizzes. So what I mean by this is after class, let's say you have 24 hours to submit your solutions to this. So this is quiz problem 1 and quiz problem 2. And I'll send an email kind of clarifying what this is in case people aren't joining us live. Sarah? Yes. Yes, everything will be posted. As always, I try to post it as soon after classes as it takes a minute to upload. Yeah, and I'll send an email. Okay, so these are important problems to understand. So the answer is it is an equivalence relation. We do have transitivity, we do have symmetry, we do have reflexivity. And so you might want to understand, so what is kind of, I'm trying to get us to start thinking about the reduction theory. Well, okay, so we have our quadratic form. I wanted to do one other thing, which was to find, let me give you an exercise. What's a good place for an exercise? How about 5-2, the 5-2 entry? Maybe I'll make this the third quiz component. I don't want to overburden you. Let's see how this works. Maybe I'll give you 2 days instead of 1. Quiz 3, find Q equivalent to, well, Q0 composed with some A, B, C, D. Q0 is our old friend 7, negative 11, 5, such that Q of 1, 0 is equal to Q0 of, how about 5, 2? 5, comma 2, 5, comma 2, which we know from our table is 85. So now I want the same answer. And again, it's not unique, but just find one Q that will capture this value. Okay? I kind of want you to do this. Well, all right. Well, we're experimenting. We're trying this out. We're going to see what works, and what makes sense for you guys. So this is your 3 problems on the quiz. Maybe 24 hours isn't enough time, so I'll give you 48 for this one. So these are the 3 quiz problems. I'll email you about the details. So we've been finding these equivalent Qs that give, and then here's the lemma, the main lemma, or maybe main theorem. The set of numbers, so let's say if Q1 is equivalent to Q2, then if you look at the set of numbers which are represented by Q1, so this is the set of integers n for which there exist x and y, integers x and y, with Q1 equal to xy of n, then this is equal to the same thing with Q2. In other words, equivalent forms represent the same numbers, i.e., equivalent forms represent the same numbers. So if we start with this new form, if we start with this form 23, 21, 5, and we start making tables just like this, we're going to see the same numbers, not in the same places. They're going to get shuffled around, but we're going to see the same numbers. So let me make that remark. What is this lemma? This lemma means this, here we go, lemma means if we had started with Q, where's one of our equivalent forms? Here, 23, 21, 5. 23, 21, 5. Instead of our Q0, 7, negative 11. Is it 5? Yeah, 5. And started and made a table and made tables of its values. What's the conclusion? Do you guys want to write in the chat what the point is that I'm trying to make? So 2 equivalent forms, I'm claiming, we're going to prove this lemma, they represent the same values. So equivalent forms represent the same numbers. So if we had started with this form, which we know is equivalent, we came up with it by composing Q0 with some invertible matrix, integer matrix. So if we had started with this form instead of this form, and made tables of its values, just like we made tables of the values of Q0, if we started making these kinds of tables, we would see the same numbers. Oh, I gave away what the punchline was supposed to be. we would see the same numbers just shuffled around. We would see the same numbers in other words, these numbers 1, 11, 5, 35, 17, 19, 7, and so on. The same numbers 1, 5, 11, 17, 7, 35, etc. But just in different places. Just in different locations. Shuffled around. In fact, that's another really good exercise. Let's think for a second. Actually, we had this other equivalent form. We started out with this form 7, negative 11, 5. But there was a kind of simpler form, 1, negative 1, 5, that was also equivalent to it. And for that form, maybe it's not so hard to make another table that looks just like this. 1, negative 1, 5. So let's use that form instead. 1, negative 1, 5. Okay? So let's see if... I don't think it's going to be that hard to make a table of these values. So before we prove the lemma, let's make a table of these values. So I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's not go too far out. So these are values of this new q, which is 1, negative 1, 5. Okay? So what is it at 1, 0? Altogether? Everybody knows the answer. It's very quick. You just read it off. Yes, it's the a value, and 0, 1 is always the c value. Awesome. Okay, we don't want the imprimitive values. Whoops. Yep, that's good. 3, 2, 4, 4, 2. 6 had a lot of imprimitivities. I think that's it for the imprimitivities. Okay, what is it at 1, 1? 1 times 1 squared minus 1 times 1 times 1. That cancels out. And 5 times xy. So that's 5. Can you guys, again, just very quickly throw out some values of this form? Just at random, grab one and compute it and tell me what it is. I'll do some also. So I'm going to do 3, 5. So when you have a value, just spit it into the chat. I picked a hard one. You guys can pick easy ones up here. Is that really right? 113. One comma 4 is 77. Very good. One five is 121. Thank you, Sriya. Anybody else got a value for me yet? Two, 1 is 7. Thank you, Wenrui. 2, 3 is 43. Thank you, Dependro. 3, 1 is 11. Three, 2 is 23. 4, 1 is 17. Let's just do 2 or 3 more and then you'll see what happens. 3, 4 is 77. Okay. Now look at these values. Here are the values of, I hope you can see them both side by side. Let's see. If I do this maybe. Can you see that? So here are their values side by side. So we have 5, 7, 11, 17, and here we have 5, 7, 11, 17. And here we have 43, 77, 43, 77. Okay, we have to go a little farther before we really see what's going on, but the values of this form are simply being shifted according to the transformation matrix, this transformation matrix, 1, 0, 1, 1. All we're doing is we're taking the values of the original form and making a change of basis, and then we're getting the same values. Okay? So anyway, that was just a little experiment for you to see what, so exercise, fill this in. Okay? But now let's prove this lemma. So again, the lemma says if two quadratic forms are equivalent, then the set of values they represent is exactly the same. Okay? Proof of lemma. It's very simple. If n is equal to q1 of xy, y is n also represented by q2. So let's say Q2 is Q1 composed with gamma. We know they're equivalent, so there's some matrix gamma, so that this is true. So what will represent what values, let's say x1, y1, where, well, the point is Q2 is Q1 composed with gamma, so this is gamma, A, B, C, D, times x1, y1. So we should take x1, y1 to be where gamma x1, y1, we want to be the original xy. Equals xy. So which x1, y1 should we take? gamma times a pair of gamma times a vector is equal to some other vector, and we want to solve for this vector. This is literally what linear algebra is for. Chic. Gamma inverse. Perfect. Gamma inverse times xy. So that's it. That's the proof. If a number is represented by q1, then how do you represent it by q2? You just evaluate it at gamma inverse of xy, because if you stick, then this will be q1 of gamma at x1, y1, which is gamma inverse xy, and this is q1 of xy. Does that make sense? So that's why they represent the same numbers. You simply make a change of variables from one to the other. Because these things are invertible and they're invertible integer matrices. Now what if they were non-invertible integer matrices? So here's a linear transformation. So this is a non-example. Non-example. This matrix. Is this matrix invertible? Sure, it has determinant 2, right? The determinant is 2 times 1, 2. So what's the inverse? So let's call this gamma. Let's see, I flip the diagonals and I negate the off diagonals. And I divide by the determinant. Thank you, Dipendro. So this matrix is a half 0, 0, 1. If you want to undo that, what does this do? It multiplies the first number by 2 and leaves the second number alone. If you want to undo that, you multiply the first number by a half and leave the second one alone. Right, and the 1/2, this is not an integer matrix. Not an integer matrix. Not integer matrix. So what? What effect does that have on quadratic forms? Well, so if we take our favorite quadratic form, x squared plus y squared, and we compose it with gamma, in other words, take 1, 0, 1, x squared, no xy's, y squared, composed with 2, 0, 0, 1, what does that do? What quadratic form does that give? Well, I'm replacing x by 2x and leaving y alone. So if I replace x by 2x and leave y alone, that gives me the form Do you guys see what's going on? Did I lose somebody? Can you write lost in the chat if you're lost? No, nobody's lost, but no one's giving me an answer. Sriya? Okay, you're a little lost. All I'm saying is what does it mean to take a quadratic form and compose it with gamma? That means I want, so let's make this quadratic form Q1, and this one is Q0. Then all I'm saying is I want Q1 applied, so I want, well, it's the same thing we've been doing all along. It's x squared plus 0xy plus y squared composed with 2, 0, 0, 1. So that's replacing x by 2x and y by y. So this is 2x squared plus y squared. That's all. And so this is the form 4, 0, 1. Right? I'm just multiplying out the 2 squared. Does that make sense to you? Okay. Now, what about this? So let's just write this out. 4x squared plus y squared. Does this represent, does Q1 represent same numbers as Q0, which was a sum of 2 squares? No, Dependro. Why not? I'm stretching it disproportionately, but it's hard to see that on the level of, you know, as a real transformation or even a rational transformation, it's not doing anything. But observe that 2 is 1 squared plus 1 squared. So 2 is represented by Q0. But how do I get 2 to be 4 times a square plus a square? If I make y equal to 1 and x equal to 0, I get 1. If I make x anything other than 0, I'm too big. Right? So that's exactly what Dependro is referring to. I'm stretching it disproportionately. This does not have determinant 1. It's not invertible. And so you can't make, even a rational change of variables does not preserve the set of represented numbers. Okay? So the lemma, this lemma is crucially a lemma about invertible integer equivalence. Okay? It's not even enough to have linear actions with, they're invertible over the rationals but not over the integers. That completely changes what numbers the quadratic form represents. Not completely, they still represent a lot of the same numbers, but if the question is, the basic question, what numbers does it represent, the form 4x squared plus y squared does not represent the same numbers as the form x squared plus y squared, even though they differ by this change of variables. Looks like an integer change of variables, but its inverse is not integer. Its determinant is not 1 or negative 1. All right. Does that make some sense? Any questions? So what we're going to do is try to understand how do we study these equivalence classes of quadratic forms under this equivalence. How do we find the simplest one, and how we can use that to understand the representation numbers. Any questions?